This is Jack Hicks, and this is my submission for Physics 2212 Lab 1 Charged Tape. So as a quick introduction, the objective was to observe and analyze a system of two charged tapes interacting and obtain position and dimension values for that system. And then using that, we can calculate the effect of gravity on each piece of tape, thus calculating the electric field on each piece of tape, finally being able to calculate the charge for each piece of tape. And we're modeling the charges and forces as, point charges and forces acting on point charges. So the main ideas are electric field and electric force. An electric field due to an object is a constant k multiplied by the object's charge and the unit vector from the source to the observation location, all divided by the magnitude of the observation vector squared. Now, if you multiply it by the object's charge itself, you get the electric force. And so the electric field will point away from the force if the charge is negative, and it'll point in the same direction if it's positive. And for the electric force, if two objects have the same charge, the electric force will be positive. If it has opposite charges, the electric force will be negative. So what we're dealing with is two same charges, and so repelling force, which can be seen later. So as a little preview, the tapes did interact. One floated above the other, and the charge on the tapes was found to be small and negative, which was about 3.76 times 10 to the negative 8th coulombs, with the electric force on one tape balancing out with the gravity force. And the system was the two tapes, the earth, the erasers, the table, literally everything, whereas the surroundings were nothing. So what models are we going to be using? So we're going to be using Newton's second law, the energy principle, and force equilibrium. So by finding the distance between the floating tape and the regular one, as well as the mass of the tapes and the dimensions of the tapes, we can find the force due to gravity, and knowing that the forces must cancel out, we find the electric force, and then use that to find the charge on each piece of tape. So we're assuming that there's no air resistance or friction, and setting the origin at the initial position of the regular tape, the one not floating, and assuming each tape has the same mass, length, charge, the charge being evenly spread across the tape, and each tape is treated as a point charge. These are all for ease of calculation, the formulas below. So our initial values are the density of the tape, the length, the mass, the separation distance between tapes, and the constants. So all of these except the density and the constants were found experimentally, which will be shown in the next slide. And so tape A is the tape above, and tape B is the tape below, and there's a diagram right there. Now, getting into the actual experiment. So here's a video of the experiment. Basically, we just put one tape below the other after kind of snapping it back with a U-tape. So we basically just taped it to the table, pulled up, and it had charge. And we put one under the other. Both were charged, and one was kind of repelled upwards. And we have a ruler to measure the distance, and this was literally the whole setup. So here's just a brief look in the code for the experiment. So basically, we have the initial values, which were shown earlier. And then we calculate the R vectors for the tapes, both from tape A to tape B and tape B to tape A. And then we calculate the magnitude of those vectors by squaring each XYZ term and taking the square root. And then we find the R hat vectors of each by taking the R vectors and dividing them by the magnitudes. And then we have the force of gravity. Each of them is the same on each piece of tape by multiplying the mass by the gravity constant. And then we know that the force of gravity must be equal to the electric force, opposite and equal, at least for the floating tape, because it's not moving. And so the force down must equal the force up, and we know there's force up. And then we can rearrange the electric force equation to obtain the charge, which is what we've done at the bottom. So taking the data and calculating the forces and charge, the force of gravity on each piece of tape is mass times acceleration, or velocity times density times acceleration, which is shown below, being negative 1.27 times 10 to the negative third newtons. And for tape A, since it's stationary, the forces must cancel. So F elect should equal negative F grab, so it's just the negative of the gravity force. Calculating the electric charge, first we use the distance we measured in the lab to get the R vector, and then rearranging the electric force equation for charge, we plug in all our numbers and get negative 3.76 times 10 to the negative 8th coulombs for our charge. So let's discuss the data. So as for discussion and conclusions, all the data has been stated before, but our model seems to agree with the observations, since a small negative charge makes sense for the tapes because it was easily lost, and it was attracted to positively charged things like myself, and repelled by negatively charged ones like the tapes repelled each other. So possible sources of error were that I didn't take into account air resistance or friction. The tapes aren't point charges and likely have different weights/dimensions. The density of the tapes are probably not exact, and there could be rounding errors or experimental errors. So some additional questions. If electrons and protons swap charges, literally nothing would happen because those are conventions we made up. As long as the charges are opposite, it doesn't matter what sign it is, and therefore the observations would be the same. Why is it important to handle the tapes as little as possible? Because if you handle it, the charges disseminate and electrons move from the tape to your hand, causing the charge to decrease.